Hi again. Welcome to a revision lecture as I promised you. I haven't received any feedback yet on last lecture, the first one. I'm very happy to receive any to be able to improve it as much as possible. Now, I haven't seen you in quite a long time, 5 or 6 weeks almost. And you have a test upcoming, whether you want to call it a midterm, a test one. I know a lot of you are very worried how this test will go, how it happen. A lot of you did not have a very strong internet connection. What I want to tell you is do not worry about all of these things, okay? The reason we are still working on this and haven't given you enough details is because we want to make sure it works perfectly when we tell you. It is going to be time limited like a normal test, but there will be flexibility if your connection disconnects for any reason. Okay, we will give you time to account for that, and there will be also flexibility in terms of when do you start. Now, naturally, this is not an assignment, this is a test, so it will take a time limited approach, but you don't have to worry if at 11 o'clock exactly you don't have an internet connection, then that's it, your test is gone. Okay, that will not happen. You have my word on it. Okay, now as for this revision lecture, this is not a one size fits all. Some people find it useful, some don't. I hope you find it useful. This is not intended as a comprehensive revision of everything we have done so far. It is we can call it an overview of what we have done so far to work as a guideline, bullet points, ru'us aqlam for what you're going to be revising hopefully soon. Okay, so what did we learn so far in this course? Well, we started with units of measurement. So this is a revision lecture. And so this is our revision lecture, okay? And the first thing we did was units of measurement. We said that everything is measured in units. We have some basic components, some fundamentals, some which are derived. The ones we are mainly concerned with in this course, we said, are mass, time, length, and a couple of others, okay? And the most important point, we said, are SI units, okay? Now, I'm underlining this twice and 2 exclamation marks because I cannot stress this enough. Whenever you do a problem, the easiest way to do it usually, especially in this course, but also outside this course, is to have all your units in one thing. Standardize all your units. Before you start plugging in numbers to equations, trying to do different things, first thing, convert everything to SI units. Okay, this will ensure you don't have unit problems. You will not have mountains that are thousands of kilometers or few hundred micrometers in length or in height. Okay, that's one. 2, we moved on from there onto how objects move. And we discussed a few key points. We discussed the idea of distance, and we discussed the idea of displacement, okay? And we said it's important to know the difference between these two. Distances add up but do not subtract. Displacements do both, okay? If I leave from my home, go all around the country, then come back again, My displacement is 0, but my distance is not 0. Okay. Then we said speed versus velocity. And again, speed comes from distance, velocity comes from displacement. Speed is only a number, velocity is a number with a direction. If a question asks you for velocity, but you just give a number without a direction, you have not answered the question. You have not given velocity, you have given speed. Okay. Then we said acceleration, and we defined acceleration crucially as something that is related to velocity, not speed. So we said things that are changing their direction, okay, even if their speed is the same. So say for example something's going in a circle, the direction keeps on changing but the speed is constant, it is still said to be accelerating. And the final thing we did was discuss the concept of average quantities versus instantaneous quantities, and we said this is crucial in some applications. Okay, the instantaneous quantity is what you see on your car speedometer when you are driving. It doesn't tell you on average how fast you have been going since you left home. It tells you right now, right at this point, what is your velocity. Or actually, the car doesn't even tell you velocity. That thing only gives you a number, so only speed. Moving on from that, we said, okay, we have constant acceleration. What do we do with constant acceleration? We said with constant acceleration, we have three main equations where we will be using them to describe how everything moves within limits, okay? Unless we go near the speed of light, most of these would work. We have equation 1, v equals u plus at. Equation 2, s equals ut plus half at squared. And equation 3, v squared equals u squared plus 2as. Now my students would be used to this notation. Some others would not be used to it, so I'm also going to write the notation that you're used to in your book. Vf equals v naught plus at. X equals v naught t plus half at squared, and vf squared equals vi squared plus 2ax. The reason I use u's and v's instead of v naughts and vf's is because I don't like having the same letter appear over and over again, but that is a personal preference. You can use whichever one of these you want. Okay, we moved on from there. Again, as I said, I'm not going to be going through detailed examples here. You have a lot of those in your book, in your slides, in your lecture notes, in your homeworks. Okay, I'm just giving an overview. From there, we took a special case. Okay, we said, okay, we are going to take a look at the case of free fall, in which the only force acting is gravity. And for that, we said our A is equal to G, and we said that is equal to 9.81 meters per second squared. And we said whether it is positive up or positive down depends on our choice of frame of reference. Okay, sometimes you can take it plus, sometimes minus, as long as once you have decided which is plus, which is minus, we cannot change it later on in the question. We have to stick with that. Okay, so next we moved on to the idea of vectors versus scalars. And we said a scalar only has a number, and a vector is two-dimensional. It has a number and a direction. Okay. What can we do with vectors? We said we can add vectors. If we have two vectors, we can add them. We said they are commutative. So if I have A plus B like this, it becomes this. We said we can subtract them, but subtracting vectors isn't like we normally subtract numbers. What we instead do is we do A plus the opposite of whatever the vector B was. This is how we subtract them. Then we came to the idea of the modulus of a vector. So we said if a vector C is equal to A plus B, okay, then actually scratch that, this might be confusing slightly. We said that the modulus of A is equal to, where A is some vector, first component squared plus second component squared plus third component squared, and then all square rooted. Okay, now the last thing we did is we said, well, before that we introduced the idea of the unit vector. We said a vector can be given as some component in the I direction plus some component in the J direction plus some component in the K direction. And we said this is called unit vector notation. Okay. Then we introduced the idea of multiplying two vectors, and we said there are two ways of multiplying two vectors, either the dot product or the cross product. The dot product is called so because we put a dot instead of a multiplication sign, and the cross product is called because we put a cross sign when we want to multiply like we normally do with numbers. But we said it is two very different things. We said that if we take A dot B, we get C, which is simply a number. Okay? It's simply a number. It's not a number with a direction. It's not a vector. Okay? However, if we do A cross B, then we get C. Okay, so how did the two multiplications worked? Well, we said the A dot B would be, what letters can I use? Okay, I will use D plus E plus F dot G. Nope, this is not going to work. I'm going to use dot L plus M plus N. We said this would be DL plus EM plus FN, and this would be just a number. On the other hand, we said if I do A cross B, I am going to end up with this sort of matrix, DEF, LMN, and we are going to have to cover the one where we want to do and then do a cross. So we are going to end up with I. So if I cover this, I'm going to have EN minus FN. So I'm going to do it with multiple colors. So this is one. So I would be EN minus FM plus J plus K. I'm just going to be preparing this way. And then for J, it's going to be DN minus FL. So DN minus FL. And then for K, I'm going to have DM minus EL. So dm minus el. And this is going to be a vectorial component. Okay, so this is the A cross B, the final result is still a vector. All right? Okay. How do we know the direction of the cross products? We said the right hand rule, A, 1. So whenever you are having a fight with someone or trying to threaten someone, you go واحد اثنين. Okay, so we're going to do the same thing, 1, 2 at right angles, and the 3 is going to be the result. So A, B, C is where the direction is. If we do it the other way around, A, B, C is going to be downwards. Okay, now we said there's an easy way to think of it. Straight is plus, reverse is minus. And the way we did it was, we said I, J, K, I, J, K, I, J, K. We're going to write it this way. Okay, and we said I cross J is plus K. J cross K is plus I. K cross I is plus J. And we said we cannot jump. And the reverse side, we said that if we do K cross J, we get minus I. J cross I, we get minus K, and so on and so forth. Okay. We then spoke about a very special case called the horizontal range. What number have I reached? Number 5. Okay. And we said we have something called the horizontal range, and the equation given by R equals V naught squared over G sine 2 theta. Okay. Now we said very important, and I'm going to write it in a danger way. Only start plus finish at same level. Only semi-circle-ish. Okay? It doesn't work for anything else. Please do not try to make it work with anything else. There is no way it works with anything else. Okay? It assumes starting and finishing at the same level. Okay? Normally just use those equations. Okay? Just use those equations. Those equations will be perfectly working well for any case whatsoever. Okay, before moving on to the next concept, which is force, okay, I have left this to the very end so that you would remember it. Okay, remember, very important, X, Y, and Z are upset. They do not speak with each other no matter what. If you have something in the x-axis and something in the y-axis, they do not speak to each other. If you have something at an angle of 45 degrees, what you can do is you can separate it into components of x and y and then treat it as if there are two separate problems without any interaction. Okay? If we try to make them interact, we will end up with problems, and the solution will be wrong. Okay, so we have reached to the next concept which we have covered, which is force. And we started by discussing the concept of inertia, which we said is the tendency of something to keep moving unless something stops it. Okay, now keep moving unless stopped. Now, next we said Newton's laws. Okay, now Newton's laws, the first law is inertia itself. Things keep moving unless stopped. And it's formally defined as things keep, never mind formally, let's talk about it the easiest way to remember it. First law of Newton is, if something is not moving, it's not going to move unless you force it to. If something is already moving, it's not going to stop unless you force it to. Okay? So in other terms, Newton's laws, first law says things are lazy. They will not move or stop unless you force them to. The second one says F equals ma, and remember, force and acceleration are both vectors. Okay, and the F equals ma says, okay, once you force them to move, they have something called mass, which tells us how much force we need to put to know how much to move. Okay, how much acceleration to give it. And the third one is what I call the universal law of تضربني بضربك. You hit me, I'll hit you back. The third law says any action has an equal and opposite direction, an equal and opposite reaction. Okay? This is like when you were little, or maybe when you're growing up, I don't know. You have a fight with someone and you tell them, if you hit me, I will hit you back. If you hit me harder, I will hit you even harder. But I'm not going to hit myself, so it's going to be in opposite direction. I'm going to hit you. Okay? These are the easiest ways I personally find to memorize or to remember these laws. Okay? Then we introduced the idea of a system as a collection of things that are treated as one. And we said we have things that are called internal forces, which are from within the system. And there are things that are called external forces that are from outside the system. And we usually use something called a free body diagram to visualize these and do our calculations. And it is important to remember, always draw a free body diagram, an FBD. Okay, always, always, always. Even if you think this is a really, really simple question, draw it. Then later on, if you don't need to use it, that's a different issue. Then we spoke about different types of forces. Okay, and we classified them into applied forces for purposes of this course. So forces where we applied, we do something. Gravitational, normal force, friction force, and the last one we discussed was tension. Okay, and we said that generally in physics and advanced physics, if you go on to do physics 2 and physics 3 and over and over, you keep going, you will eventually learn that everything in the universe is all the forces are part of 4 forces. Okay, everything is classified as one of 4, which are the strong force, the weak force, the electromagnetic force, and gravitational forces. Now, 1, 2, and 3 are not in this course. This is in our course. I just wanted to tell you, well, to give you something to look forward to, that those rest of those forces are actually usually one of those 3 forces, and mostly actually electromagnetic. The strong and weak forces are only applied when you're going to subatomic levels, very, very tiny things. Okay. Then we expanded upon the idea of friction, and we said this is due to microscopic forces, because nothing is really smooth. So as smooth as you are, when 2 things touch each other, they start going, they have forces that are grooves, and those grooves cause forces to go between them. And we said friction is either mu SFN or mu KFN. Okay, and we said that mu K is generally less than mu S. We then discussed circular motion, where we said the force to keep something going in a circle of F equals mv squared over r, and the acceleration is v squared over r. Okay. From there on, we moved on to, we left forces alone a little bit, and we went to the idea of work, energy, and now, as you're all aware, energy and work isn't actually in the midterm and test 1, but since it's a revision lecture, I might as well do everything that we have done up until this point. So, we said energy and work can be changed, cannot be created or destroyed. Okay, and we discussed some types, like the kinetic energy, half mv squared, like the gravitational potential energy, mgh, like the elastic potential energy, half kx squared, and all of these came from a general rule that work equals F dot T, which is Ft cosine theta. And we said it can be positive or negative, giving energy to system or taking energy from system. We then said that if we have a variable force, then our work is going to be the integral of the function of the force with the distance. And finally, we said the idea of the work energy theorem to be that the work equals the change in energy, which is the collective change in energy of everything in that system. and we said this is equal to 0 if isolated. Okay. Now, some students have emailed me, some students have come to me before the semester and before, well, we stopped the semester for the coronavirus, and asked me what's the point of all of this work thing. Why do we care about work energy? We have everything we can do everything with the laws that we did before learning about energy or about work. I can calculate my forces, I can do my final velocities, my initial velocities. Why bother? And my answer to that would be, and this would be the last thing we do today, is that it gives us an alternative route. Sometimes it's good to have a different route to do something. And actually, often in advanced physics, we find that dealing with energy is way better than trying to, find the position and velocity of every single particle and tracing it. And I'll give you one very, very quick example. Okay. Say, for example, we have this water slide. Okay, we did something similar in yesterday's lecture. And we have something here at the very top which wants to come here, and we want to know what is the final velocity. Fine. Now, this is, as you can see, this is not a straight line. Yeah, this is a very, very wavy line, which means that if I want to actually do f dot t, or if I want to find the total distance and calculate the velocity and the acceleration, everything, and all the forces at every single point, this is going to be a nightmare of a calculation. Yet, I can do it in a single line, just one line. How? I know that the total energy, oops, what did I just do? Okay, I haven't lost everything, yay. Go back, keep going. Okay. The easiest thing for me here is to see my total energy up here is simply potential energy. It's not moving, it's not doing anything else, so it's simply mgh. There's no friction or anything else. If there is friction, I can factor it into this equation. But if there's no friction or anything else, then the simplest thing I can do is say my total energy here is simply kinetic energy, half mv squared. Which means if I want to calculate my final velocity, all I do is mgh equals half mv squared. The m's cancel, and I get v squared equals 2gh. So v is equal to square root of 2gh, and voila. I did not need to do any long calculations. Everything done in one line. Well, 3 lines, but that's because I'm writing it all out. Okay, so I hope this was useful. Any questions, any feedback, as usual, email. Or if you want, you can comment. If you're watching it on YouTube, you can comment. If you're downloading it from Moodle, then yeah, email. Okay. For those of you who don't know, these videos can be accessed on both Moodle and YouTube. YouTube gives you different resolutions, high resolutions, low resolutions. Moodle gives you one resolution. You have to download it, but that download is free, because Umantel and Uridu have both announced that anything ending with .edu.om is free to browse. Okay, I